Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The ancient Greek philosopher Aristotle gazed upward at the night sky in the 4th century BCE, constructing a cosmological model that would dominate Western thought for nearly 2 millennia. His universe consisted of concentric crystalline spheres, each carrying celestial bodies in perfect circular motion around a stationary Earth. This wasn't merely observation, it was philosophy meeting physics, establishing the first systematic attempt to understand the cosmos through reason and logic. Aristotle's model reflected deeper philosophical principles. He believed in the perfection of celestial motion, arguing that the heavens operated according to different physical laws than the terrestrial realm. So the sublunary world, everything below the moon, was characterized by change, decay, and linear motion. Above this boundary, the celestial realm exhibited eternal, unchanging circular motion. This dichotomy between earthly imperfection and celestial perfection would profoundly influence cosmological thinking for centuries. The geocentric model wasn't simply wrong, it was sophisticated. Aristotle's student, the astronomer Hipparchus, and later Claudius Ptolemy in the 2nd century CE, refined this system with epicycles and deference to account for the complex motions of planets. Ptolemy's Almagest became the definitive astronomical text, demonstrating how philosophical frameworks could generate predictive mathematical models. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Medieval Islamic scholars inherited and transformed Greek cosmology. Figures like al-Battani in the 9th century and al-Biruni in the 11th century made precise observations that would later prove crucial for Copernican astronomy. They didn't merely preserve ancient knowledge, they actively questioned and refined it. Ibn al-Haytham, known in the West as al-Hazan, developed sophisticated mathematical models while maintaining the philosophical framework of celestial perfection. The tension between observation and philosophical commitment became increasingly apparent. Medieval astronomers noticed discrepancies between Aristotelian theory and careful observation. The moon's cratered surface, visible to the naked eye, challenged the notion of celestial perfection. Comets appeared to move through the supposedly solid crystalline spheres. These anomalies created cognitive dissonance that would eventually fracture the ancient worldview. Thomas Aquinas in the 13th century attempted to reconcile Aristotelian cosmology with Christian theology, creating a synthesis that placed God as the prime mover of the celestial spheres. This integration of philosophy, astronomy, and theology created a comprehensive worldview where understanding the cosmos meant understanding divine purpose. The universe wasn't just a physical system, it was a moral and spiritual hierarchy reflecting divine order. The scholastic tradition established crucial methodological principles that persist in modern cosmology. The emphasis on logical consistency, mathematical precision, and systematic observation created intellectual tools that would prove essential for the scientific revolution. Medieval scholars demanded that cosmological models be both observationally adequate and philosophically coherent, a requirement that contemporary cosmologists still face when dealing with dark matter, dark energy, and quantum mechanics. By the 14th century, cracks in the Aristotelian edifice were becoming impossible to ignore. Nicole Oresme questioned whether the Earth's rotation might explain apparent celestial motion. Jean Buridan developed impetus theory, challenging Aristotelian physics. These weren't merely technical adjustments, they represented fundamental philosophical shifts about the nature of motion, space, and the relationship between mathematics and physical reality. The ancient and medieval periods established cosmology as both an observational science and a philosophical discipline. This dual character, empirical investigation guided by metaphysical commitments, continues to define cosmological inquiry. Modern debates about the multiverse, the anthropic principle, and the nature of physical laws echo ancient questions about cosmic purpose, mathematical beauty, and the relationship between mind and cosmos. Understanding this historical foundation illuminates why contemporary cosmology remains as much philosophy as physics. Nicholas Copernicus stood at the threshold of a cosmological revolution when he published De Revolutionibus Orbium Coelestium in 1543. His heliocentric model wasn't primarily motivated by superior observational accuracy. It was driven by philosophical aesthetics. Copernicus found the complexity of Ptolemaic epicycles aesthetically displeasing and sought mathematical simplicity. By placing the Sun at the center, planetary motions became more elegant, though not necessarily more accurate in predicting celestial positions. The Copernican revolution represented more than astronomical reform. It constituted a fundamental shift in humanity's cosmic perspective. Earth was no longer the center of creation, but merely another planet orbiting an ordinary star. This demotion challenged not just scientific theory, but religious cosmology, philosophical anthropology, and humanity's sense of cosmic significance. The implications rippled through every aspect of intellectual life. Galileo Galilei's telescopic observations beginning in 1609 provided the first direct evidence supporting Copernican theory. His discovery of Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, proved that celestial bodies could orbit something other than Earth. The phases of Venus demonstrated that this planet orbited the Sun, not Earth. These weren't philosophical arguments, but empirical observations that decisively challenged geocentric assumptions. Galileo's conflict with the Roman Catholic Church illustrated the broader cultural tension surrounding cosmological change. The Church's opposition wasn't merely religious conservatism, it reflected legitimate concerns about the implications of infinite space and the plurality of worlds. If Earth wasn't unique, what distinguished humanity's spiritual status? These questions remain relevant in contemporary discussions about extraterrestrial life and the cosmic significance of consciousness. Johannes Kepler's three laws of planetary motion, formulated between 1609 and 1618, completed the mathematical foundation of modern astronomy. His discovery that planets move in elliptical, rather than circular orbits, violated 2 millennia of assumptions about celestial perfection. Kepler's work demonstrated that mathematical description could be more fundamental than philosophical. Preconceptions about cosmic harmony. The transition from circular to elliptical orbits represented a crucial methodological shift. Ancient and medieval astronomers had prioritized geometric perfection over observational accuracy. Kepler reversed this priority, allowing mathematical relationships discovered through careful observation to override aesthetic preferences. This methodological revolution established empirical adequacy as the primary criterion for cosmological theories. Isaac Newton's Principia Mathematica, published in 1687, synthesized terrestrial and celestial mechanics into a unified physical theory. Newton's law of universal gravitation explained both falling apples and planetary orbits through the same mathematical principles. This unification eliminated Aristotle's distinction between sublunary and celestial physics, establishing the universe as a single mathematically governed system. Newton's cosmology introduced new philosophical challenges. If gravitational attraction operated instantaneously across infinite distances, how could this be reconciled with mechanical causation? Newton himself was troubled by this action at a distance, proposing that gravity might be mediated by an ethereal medium. These concerns anticipate contemporary debates about quantum entanglement and the nature of space-time. The Newtonian universe was deterministic, predictable, and fundamentally mechanical. Pierre-Simon Laplace famously argued that a sufficiently powerful intelligence could predict the entire future of the universe from complete knowledge of present conditions. This mechanical determinism shaped Enlightenment philosophy, suggesting that rational inquiry could eventually explain all natural phenomena through mathematical laws. Newtonian cosmology also raised profound questions about cosmic purpose. If the universe operated according to deterministic physical laws, what role remained for divine providence or cosmic teleology? Some thinkers, like Gottfried Leibniz, argued that mathematical harmony itself reflected divine wisdom. Others, like Denis Diderot, suggested that mechanical explanation eliminated the need for cosmic purpose entirely. The success of Newtonian mechanics established physics as the fundamental science, with astronomy as its most successful application. This reductionist approach suggested that all natural phenomena could ultimately be explained through the motion of particles governed by mathematical laws. The mechanistic worldview dominated scientific thinking until the quantum and relativistic revolutions of the 20th century, and its influence persists in contemporary cosmological modeling and the search for a theory of everything. Albert Einstein's general theory of relativity, published in 1915, fundamentally transformed humanity's understanding of space, time, and gravity. Unlike Newton's absolute space and time, Einstein revealed space-time as a dynamic, four-dimensional fabric that could be curved, stretched, and warped by matter and energy. This wasn't merely a technical refinement, it represented a complete reconceptualization of cosmic architecture. Einstein's field equations described how matter and energy determine space-time curvature, while space-time curvature determines how matter and energy move. This elegant reciprocity eliminated the Newtonian mystery of action at a distance. Gravity wasn't a force transmitted across space, it was the curvature of space-time itself. Planets orbit stars not because they're pulled by invisible forces, but because they follow the straightest possible paths through curved space-time. The cosmological implications of general relativity emerged when Einstein applied his equations to the universe as a whole. In 1917, he developed the first relativistic cosmological model, assuming a static, homogeneous universe filled with matter. However, his equations predicted that such a universe would either expand or contract. It couldn't remain static. To preserve cosmic stability, Einstein introduced the cosmological constant, a repulsive force that could balance gravitational attraction. Alexander Friedmann's work in 1922 revealed that Einstein's static universe was unstable. Any small perturbation would cause it to expand or collapse. Friedmann's solutions to Einstein's field equations described universes that could be expanding, contracting, or oscillating. These mathematical models suggested that the cosmos itself had a dynamic history, challenging the ancient assumption of cosmic permanence. Georges Lemaitre independently developed similar solutions and proposed that the universe began in a primordial state of extreme density and temperature. In 1927, he suggested that the recession of galaxies observed by Vesto Slipher could be explained by cosmic expansion. Lemaitre's hypothesis of the primeval atom became the foundation of Big Bang cosmology. Edwin Hubble's observations in 1929 provided decisive evidence for cosmic expansion. Using the 100-inch telescope at Mount Wilson Observatory, Hubble measured the distances to nearby galaxies using Cepheid variable stars as standard candles. He found that more distant galaxies were receding faster, establishing Hubble's law, recession velocity is proportional to distance. This relationship implied that space itself was expanding uniformly in all directions. The expanding universe concept revolutionized cosmological thinking. If the universe was expanding now, it must have been smaller and denser in the past. Extrapolating backward suggested that the cosmos began in a state of infinite density and temperature, a cosmic singularity. This prediction introduced profound philosophical questions about cosmic origins, the nature of time, and the possibility of creation ex nihilo. Einstein initially resisted the expanding universe, calling the cosmological constant his greatest blunder. However, the accumulating observational evidence eventually convinced him that cosmic expansion was real. The static universe he had, preferred for philosophical reasons, eternal, unchanging, and self-contained, gave way to a dynamic cosmos with a definite beginning and an uncertain future. The Big Bang theory, as it came to be known, faced significant challenges. If the universe began as a singularity, what caused the initial expansion? How did the smooth, hot plasma of the early universe evolve into the complex structure of galaxies, stars, and planets? These questions drove theoretical developments in particle physics, thermodynamics, and quantum mechanics throughout the 20th century. General relativity also predicted exotic cosmological phenomena that seemed purely theoretical in Einstein's time. Black holes, gravitational waves, and the bending of light by massive objects were mathematical curiosities until technological advances made their detection possible. The recent observations of gravitational waves by LIGO and the imaging of black holes by the Event Horizon Telescope demonstrate the continuing relevance of Einstein's insights. Modern cosmology emerged from the marriage of general relativity with quantum mechanics and particle physics. The standard model of cosmology describes a universe that began with rapid inflation, underwent nucleosynthesis to form light elements, became transparent when electrons combined with nuclei, and evolved through gravitational collapse to form the cosmic web of galaxies and dark matter. This synthesis of Einstein's geometric vision with quantum physics continues to guide cosmological research, from the search for dark energy to the quest for quantum gravity. The quantum revolution began in 1900, when Max Planck proposed that energy was emitted in discrete packets called quanta. This seemingly minor technical adjustment to blackbody radiation theory would ultimately undermine the entire edifice of classical physics. Planck himself initially viewed quantization as a mathematical trick rather than a fundamental feature of nature. However, the quantum concept proved to be the key to understanding atomic structure, chemical bonding, and the very foundations of matter and energy. Albert Einstein's 1905 explanation of the photoelectric effect demonstrated that light itself was quantized into particles called photons. This wave-particle duality challenged the classical assumption that phenomena could be classified as either waves or particles. Light exhibited both characteristics depending on the experimental setup, suggesting that the classical categories of physics were inadequate to describe microscopic reality. Niels Bohr's atomic model, developed in 1913, introduced quantum mechanics into cosmology through stellar nucleosynthesis. Stars shine because quantum tunneling allows protons to overcome electromagnetic repulsion and fuse into heavier elements. Without quantum mechanics, stellar cores wouldn't be hot enough to sustain nuclear fusion, and the universe would be dark and lifeless. The quantum nature of matter directly enabled the cosmic processes that created the chemical elements necessary for planets and life. Werner Heisenberg's uncertainty principle, formulated in 1927, revealed fundamental limits to simultaneous knowledge of particle properties. Position and momentum, energy and time, cannot be measured with arbitrary precision simultaneously. This wasn't merely a limitation of measurement technology. It reflected the inherent probabilistic nature of quantum reality. The deterministic universe of Laplace became impossible even in principle. The Copenhagen interpretation of quantum mechanics, developed by Bohr and Heisenberg, suggested that quantum systems exist in superposition states until measurement causes a wave function collapse. This interpretation introduced consciousness or observation as a fundamental element in physical processes. Some cosmologists speculated that the universe itself might require conscious observers to define its properties, a radical departure from the objective, observer-independent cosmos of classical physics. Quantum mechanics transformed our understanding of the cosmic vacuum. Rather than empty space, the quantum vacuum teems with virtual particle pairs that spontaneously appear and annihilate. These quantum fluctuations have measurable effects, such as the Casimir force between conducting plates. The vacuum possesses energy density that could potentially drive cosmic inflation or dark energy acceleration. The many worlds interpretation, proposed by Hugh Everett III in 1957, suggested that quantum superposition never collapses. Instead, each quantum measurement splits the universe into multiple parallel realities, each corresponding to a different measurement outcome. This interpretation eliminates the special role of conscious observers, but postulates an infinite multiverse of parallel universes, a cosmological consequence of quantum mechanics. Quantum cosmology emerged in the 1960s when physicists began applying quantum mechanics to the universe as a whole. The Wheeler-DeWitt equation attempts to describe the quantum state of the entire cosmos, though its interpretation remains controversial. Does the universe exist in quantum superposition? Until observed, who or what could observe the universe from outside? These questions challenge conventional assumptions about cosmic reality. Stephen Hawking's work on black hole thermodynamics revealed profound connections between quantum mechanics, gravity, and cosmology. Hawking radiation emerges from quantum fluctuations near black hole event horizons, causing black holes to evaporate over time. This process violates classical general relativity, which predicted that black holes could only grow larger. The information paradox arising from black hole evaporation continues to challenge physicists' understanding of quantum gravity. Cosmic inflation theory, developed by Alan Guth in 1980, relies on quantum fluctuations to explain cosmic structure. During the inflationary epoch, quantum uncertainties in the inflaton field were stretched to cosmic scales, providing the seeds for galaxy formation. These quantum fluctuations are now observable as temperature variations in the cosmic microwave background radiation, detected by satellites like the Cosmic Background Explorer and Planck. The anthropic principle, particularly its strong version, suggests that the universe's fundamental constants are fine-tuned for the existence of observers. Some interpretations combine this with quantum mechanics to propose that conscious observation selects our particular universe from the quantum multiverse. This observer selection effect could explain why we find ourselves in a universe capable of supporting life and consciousness. Contemporary quantum cosmology continues to grapple with fundamental questions about the nature of reality, consciousness, and cosmic origins. Proposals for quantum gravity, such as loop quantum gravity and string theory, attempt to unify quantum mechanics with general relativity. These theories suggest that space-time itself might be quantized, potentially resolving the Big Bang singularity and providing new insights into the ultimate nature of cosmic reality. The late 20th century brought cosmological discoveries that fundamentally challenged humanity's understanding of cosmic composition and structure. In 1973, Vera Rubin's observations of galaxy rotation curves revealed that spiral galaxies contain far more mass than visible matter could account for. Stars in the outer regions of galaxies were moving too fast to remain gravitationally bound, unless invisible dark matter provided additional gravitational attraction. This discovery suggested that luminous matter represents only a small fraction of cosmic mass. Dark matter's existence was confirmed through multiple independent observations. Gravitational lensing studies showed that galaxy clusters bend light more strongly than their visible matter could explain. The cosmic microwave background radiation exhibits acoustic oscillations that require dark matter to explain their amplitude and spacing. Large-scale structure formation simulations reproduce observed galaxy distributions only when dark matter is included. Despite overwhelming evidence for its existence, dark matter's fundamental nature remains mysterious. The accelerating expansion of the universe, discovered independently by the Supernova Cosmology Project and the High-Z Supernova Search Team in 1998, revealed an even more profound mystery. Type Ia supernovae at high redshifts appeared dimmer than expected in a matter-dominated universe, indicating that cosmic expansion was accelerating rather than decelerating. This acceleration requires a repulsive force stronger than gravitational attraction, dubbed dark energy. Dark energy comprises approximately 68% of the universe's total energy density, while dark matter accounts for 27%. Ordinary matter, everything made of atoms including stars, planets, and life, represents only 5% of cosmic composition. This revelation was humbling. The universe is dominated by phenomena that remain completely mysterious despite centuries of scientific progress. The cosmological constant, Einstein's greatest blunder, suddenly became relevant again. The simplest explanation for dark energy is vacuum energy. The quantum fluctuations of empty space However, theoretical calculations predict a vacuum energy density that is 120 orders of magnitude larger than observations allow. This cosmological constant problem represents one of the most severe discrepancies between theory and observation in all of physics. Alternative explanations for dark energy include quintessence fields, modified gravity theories, and the possibility that our understanding of cosmic expansion is fundamentally flawed. Some theories propose that dark energy is not constant but evolves over cosmic time. Others suggest that gravity itself behaves differently on cosmic scales than Einstein's general relativity predicts. These investigations continue to challenge the foundations of theoretical physics. The multiverse hypothesis emerged from attempts to explain cosmic fine-tuning and the anthropic principle. If fundamental constants like the strength of gravity, the mass of the electron, or the cosmological constant were slightly different, stars, planets, and life could not exist. The apparent fine-tuning of these parameters for the existence of complexity and consciousness raises profound questions about cosmic purpose and design. Eternal inflation theory, developed by Andre Linde and others, suggests that our observable universe is one bubble in an infinite cosmic foam. Different bubbles could have different physical laws, fundamental constants, and dimensionality. The anthropic principle then explains why we observe a life-permitting universe. We exist only in bubbles, where the constants allow for stars, planets, and biological evolution. String theory's landscape problem compounds the multiverse discussion. String theory suggests that there may be 10 to the 500th power different possible vacuum states, each corresponding to a different set of physical laws and constants. If all these possibilities are realized somewhere in the multiverse, then our universe's apparent fine-tuning becomes a selection effect rather than evidence for cosmic design. The many-worlds interpretation of quantum mechanics provides another pathway to the multiverse. If every quantum measurement splits reality into parallel branches, then all possible outcomes occur in different parallel universes. The quantum multiverse would contain every possible history and every possible future, making our particular cosmic trajectory just one thread in an infinite tapestry of realities. Contemporary cosmology faces unprecedented challenges in distinguishing between science and philosophy. Multiverse theories make predictions that may be inherently unverifiable. How can we test hypotheses about parallel universes that are causally disconnected from our own? Some philosophers of science argue that untestable multiverse theories fall outside the domain of empirical science, while others contend that theoretical elegance and explanatory power justify their consideration. The journey from Aristotle's crystalline spheres to contemporary multiverse theories reveals cosmology's evolution from a primarily philosophical discipline to a mathematically sophisticated empirical science. Yet fundamental questions persist. Why does the universe exist? Why do the laws of physics take their particular forms? What is the ultimate nature of space, time, and matter? These questions ensure that cosmology remains as much philosophy as physics, bridging the gap between scientific methodology and humanity's deepest concerns about existence, purpose, and cosmic meaning. As we stand at the threshold of new discoveries from the James Webb Space Telescope and gravitational wave detectors, the cosmic conversation between philosophy and physics continues to evolve.